We'll start in 2 minutes. Okay, we'll start now. Okay, welcome you all back to the problem solving session for the NPTEL course Fluid and Particle Mechanics. And the course code is NOC25CH49, and we are in week 9 for the sessions. So the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras, and the live sessions where we solve problems are handled by myself, Kartika. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So moving on, this Fluid and Particle Mechanics course is a 12 weeks course. So this is the course syllabus. Even though we are not exactly moving according to it, we have almost covered the basics like introduction to Navier-Stokes equations, dimensional analysis, and turbulent flows, which we'll see today, and packed beds and fluidized beds filtration, and motion of a particle, terminal velocity. So those things and all we have seen. So in today's class, what we are okay. Before moving to today's session, we'll just see the books and references. First one is Unit Operations of Chemical Engineering, which most of us would be aware of, written by Warren Lee McCabe, Julian Cleveland Smith, Peter Harriot. And next is Fluid Mechanics by Frank M. White. And third, Introduction to Particle Technology by Martin J. Rhodes. And few references are Coulson and Richardson's Chemical Engineering, Fluid Mechanics by Piyush K. Kundu, and Principles of Colloid and Surface Chemistry by Paul C. Heymans and R. Rajagopalan. Finally, it is Transport Phenomena by Bird Stewart Lightfoot. So now actually we have almost covered 2/3 of the course, only 1/3 is left out. So in week 9, what we are going to see is turbulent, laminar and turbulent flows, and followed by turbulent stress and turbulent shear layers, and turbulent flow near a wall and in a pipe. So these are the topics which you will be seeing in today's class. I mean, topic in the sense not of theory, but problems related to these topics. So first question, now we'll start with the problems directly. So question 1, it is about water is flowing in a pipe at 2.71 meter cube per minute between points A and B. A mercury manometer is connected between these 2 points and it gives a reading of 135 mm. The length of the pipe between points A and B is 5 meters and the pipe diameter is 6 centimeter. However, the pipe is not horizontal but rather the point B is 1 meter above point A. It is given that pressure at point A is higher than point B. Assume room temperature. So what is given? We are asked to find okay, we are not asked to find anything this is just a statement, beginning statement. So we are given that water is flowing in a pipe. So consider a pipe where water is flowing from one end to the other. So one end is A and the other end is B. So in between these 2 points we are connecting a manometer to measure the pressure drop inside the pipe. And it is like 2 point. Okay, like here we are not given from which direction the water is flowing, rather other few information is given, like the water flow rate is 2.71 meter cube per minute. So it is 2.71 meter cube per minute, which we can convert it into meter cube per second by dividing it by 60. So we know flow rate and we have the mercury manometer connection and we know the height difference in the mercury manometer reading. So with that we can calculate the pressure drop. So again it is 135 mm and length of the pipe where the flow is taking place is given as 5 meters and the diameter of the pipe is 6 centimeter. Also it is given that pipe is not horizontal, it is not straight but rather pipe B is slightly higher than, sorry, point B is slightly higher than point A. So if it is, B is lower than A, we can straight away say like how the flow will be. But rather in this question what is given, B is slightly above point A. So it means that the pipe is not a straight pipe, rather it is like a slightly inclined pipe, that is one thing. And also the height difference, the second point B is above 1 meter above point A. And we know the flow rate, that is 2.71 meter cube per minute. So with that information, let us see what is asked in question. The direction of the flow is from dash. Option A from A to B. Option B from B to A. Option C, not enough information to predict the direction, but direction is not needed for calculations. Option D, it can be either way but the direction is not needed for the calculations. So actually what is asked in the question is, we are asked to find out from which direction, that is from which point to which point the flow is happening, or if at all it is necessary to know that, or we can get away without calculating that. So basically we need to know the direction in which the flow is happening, only then we can use signs in further problems and it will be easy. So here there are two things given. First, it is like A and this is B. Like this is A and this is B. So there is some 1 meter height difference between the A and B point. And what else is given? Flow rate is given as 2.71 meter cube per minute. And we are connecting a mercury manometer and the height difference in the mercury manometer is also given. Like generally it will be like this, right? This is filled with mercury. So this height difference is also given as 135 mm. So with that we need to find out whether flow is happening from point A to B or from point B to A. That is the simplest question, because we need the direction, so we can straight away eliminate C and D. So that information, first we'll see, like actually like one direct hint given over here is pressure at A is higher than point B. So pressure at A is higher than point B. So it means that flow will happen from A to B. So we can straight away say that. So answer is option A. From A to B is the right answer. So to look more in depth into it, we'll see what are all the calculations which we can do and what are all the other inferences we can get. So basically, on looking at the question, we can say that flow will happen from A to B. Now, first let us write given. Flow rate Q is given as 2.71. There is okay 2.71 meter cube per minute, and what we need to do is we need to convert it into meter cube per second to maintain unit consistency. So we are dividing it by 60. If we divide, what we will get? We will get 0.0452 meter cube per second. And next is density of water. Was it given that water is a fluid? Yeah, water is the fluid here. So we need to know the density and viscosity of water. Density of water is 1000 kg per meter cube, and viscosity we haven't given, but it is 0.001 kg by meter second. Viscosity of water. It is 10 power 3. Viscosity is 10 power minus 3. And next is mercury manometer reading. It is given as 135 mm, or in other words, in other units, it is 0.135 meter. And density of mercury also we know as 13,600 kg per meter cube. Pipe length between points A and B is given as 5 meters. And pipe diameter is given as 6 centimeters. So it is 0.06 meter. And elevation difference, B is higher than A. So ZB minus ZA is 1 meter. Point B is 1 meter above point A. Pressure at point A is higher than at point B. These are all the things given in the question. And this is not because we already did it. We already wrote row. So we can directly go to the next one. So manometer reading indicates the pressure difference between point A and B. So PA minus PB can be given by rho GH. So here rho is density of mercury. So pressure at A is higher than pressure at B. Mercury column height corresponds to this difference. So we can substitute everything. G is 9.81 meter per second square. So PA minus PB becomes 13,600 into 9.81 into H. So H is the difference in the mercury level in the manometer. So that was 135 mm or 0.135 meter, which gives us 18,011 0.16 Pascal. So that is the pressure difference between point A and B. So flow direction will be based on pressure difference and the elevation difference. So if we write Bernoulli equation between points A and B, what will we get? PA plus rho G ZA plus half rho VA square equal to PB plus rho G ZB plus half rho VB square plus HF. So if we take a velocity to be same almost between 2 points, what else will be left with? PA minus PB equal to half rho VB. Okay, this one we have cancelled. So it will be rho G ZB minus ZA plus HF. And rho G ZB minus ZF will be equal to ZB minus ZA is 1 meter. Rho is water, so it is 1000. So 1000 into 9.81, it is 9810 Pascal. Also, what is given in the question? In the question, it is given that pressure at point A is higher than point B. Also, water flows from region of higher pressure to the region of lower pressure. Additionally, if we look at point B is higher than point A, which means elevation difference is height. Like point B is higher than point A. So this difference will kind of oppose the flow, which normally should be happening from A to B. But in spite of this elevation increase, the pressure at A is higher. So the flow will be from A to B to overcome that elevation head. So that is the thing. So on looking at it, we can say, on looking at the question itself, we can say that the direction of flow might be from A to B. But in order to confirm our theory, we are just doing the basic calculations. So we first found out the manometer pressure difference, and what did we get? We got 18,011 Pascal, and later we did the pressure, use the Bernoulli equation, and we got the head, and it is found as 9,810 Pascal, and in the question already it is given that point A is at a higher pressure than B. So we are concluding that water flows from a region higher pressure region to the region of lower pressure, that is from A to B. Also, point B is 1 meter above point A, but there is a height difference. But despite this height difference, pressure at A is higher, so flow will move from A to B to overcome the elevation head. So one thing I would like to say is, if there is any numerical error in the questions, please cross check yourself when you are if you are finding it during solving, because I just changed the questions, so there might be some calculation error which might occur, like in spite of me checking it once thoroughly. Sometimes it may happen, so just like if you are finding anything wrong, please let me know. So that is for question 1. Next we have question 2. If flow is assumed to be laminar, imagine you are in a world of zero disturbances and you have automatically smooth pipe that flow can remain laminar for any Reynolds number, then the friction factor can be calculated as dash. So we are they are saying that if flow is assumed as laminar flow, we automatically have a okay. This is not atomically, so I'm just removing it. We have smooth pipe that flow can remain laminar for a longer for any Reynolds numbers. So based on that assumption, we need to calculate the friction factor, and we are given few options. Option A, it is 0.0000667. Option B, it is 0.000667. Option C, it is 0.00667. Option D, it is 0.00000667. So the right answer is actually option A is the right answer. So what is given, how to calculate it? Flow, we are asked to assume it is laminar, like it is, they are asking us to assume by considering it as an ideal world where there is zero disturbances and we have a smooth pipe. So in that case, the flow can be remaining laminar for a longer period of time. So what will be the friction factor calculated under such condition? So friction factor is actually given by F is equal to 64 by Re, and this is for laminar, but since in the question it is explicitly mentioned that assume the flow to be laminar, we are just assuming it. So it is 64 by Re. So to find Re, what we need? We need rho V d by mu. So in the question it is given that it is a continuation of previous question. So it is water and it is okay, Reynolds number we actually calculated, right? No. Okay, Reynolds number is equal to 2.71 meter cube per minute. Okay, so basically F is given by 64 by Re and Re is given by rho Vd by mu. So for rho we know it is water and mu also we know under the same condition that it is a water. Now we are left with V and D. So it is V is velocity which we can get from the flow rate and D is the pipe diameter. So it is Q is equal to 2.71 meter cube per minute. Yeah, it is 2.71 meter cube per minute, and therefore we are dividing it by 60. What will we get? 2.71 divided by 60, 0.0452, and mercury manometer reading is 0.135 meter. Pipe length between A and B is 5 meters and pipe diameter is 0.06 meters. Elevation difference, again this given conditions are similar to the problem that we saw last. So it is 1 meter, point B is in 1 meter above A. So pressure at point A is higher than the pressure at point B. So now what we need to do, we need to first find V and rho and mu. So cross sectional area is given by A is equal to pi by 4 d square. So it is pi by 4 into 0.06 meter square. What will we get? Sorry, 3.14 divided by 4 divided by 0.06. 13 point, oh, 3.14 divided by 4 into 0.06 square into. So it is 2.8 into 10 power minus 3, which is slightly given here. So these are all the things. V is equal to Q by A. Like once we find find Q, we need to find A. So it is 2.8 into 10 power minus 3 meter cube per second. Oh, sorry, meter square. Now we need to find velocity. For that, what we are going to do, we are going to divide the flow rate by cross sectional area. So flow rate is 0.0452 divided by this one, 15.99 meter per second, and viscosity is given as 0.001 kg by meter second. So now we need to substitute it into Reynolds number. So Reynolds number formula is rho v d by mu. So it is 1000 into 15.99 into 0.06. Yeah, 0.06 meters divided by 0.001. It is 959,400. It is 0.000006. Oh, sorry, 0.00067. So that is the friction factor. So head loss. Okay, it is assumed to be laminar. Then the friction factor can be calculated as C dash. So it is 0.000006. Oh, sorry, 4 zeros followed by 667. 6.67 into 10 power minus 5. Basically, I can do that. Okay, sorry, this is friction factor. So it does not have unit actually. I think I confused. Yeah, it is 6.67 into 10 power minus 5, but it doesn't have unit because it is a friction factor. Right, yeah. So now we will go to question 3 actually. In question 3, what is asked? Head loss in meters. So we need to find HF. HF is given by FLV square by D2G. So in this we need to substitute everything. So F we calculated it as 6.67 into 10 power minus 5. L is 5 meters and V is 15.99 square divided by D2G. So D is 0.06 meters to G is 9.81. So what are we getting on substitution? 6.67 into 10 power minus 5 into 5 into 15.99 square divided by 0.06 divided by 2 divided by 9.81. So it is 0.0724 meters. So that is the friction head loss in meters. So I mean it is just a direct substitution actually. Formula and later it is solution. Question 3 is that now we'll go to question 4. In question 4, what is asked? Water at 20 degrees Celsius flows through a pipe at 0.02 meter cube per second with a friction head loss of 12.95 meter. The power required to drive this flow is dash kilowatts. So actually water at 20 degrees Celsius flows through a pipe at a flow rate of 0.02 meter cube per second and it is having a friction head loss of 12.95 meter HF, and we are asked to find the power required to drive this flow and we are asked to find the answer in kilowatts. Since this is a numerical problems, please make sure you are writing your answer in the proper unit, otherwise your answer may be right but it may not be the proper according to the unit. So just check with that. So now what are we asked? We have to calculate the power required. So power is actually QGHF into rho. So rho is density of water, it is 1000 kg per meter cube and Q is given as 0.02 meter cube per second and G is 9.81 and HF is given as 12.95. So it is a direct substitution. So we'll see. First, given flow rate in that is Q is 0.02 meter cube per second and head loss HF is 12.95 meters, and third one water at 20 degrees Celsius, and okay we can mention density and gravity. Density of water is 1000 kg per meter cube and acceleration due to gravity G is 9.81 meter per second square. And formula as I mentioned, it is rho G Q into HF. So rho is 1000, G is 9.81, Q is 0.02 meter cube per second, HF is head loss in meters, so it is 12.95 meters. So we have to now substitute everything in the original formula. So what will we get? Will be like 1000 into 9.81 into 0.02 into HF is 12.95. It is 2540.79 and it is power. And what will be the unit? It is kg per meter cube into meter per second square. So we can like calculate it. Not laser pen. So rho is kg by meter cube and G is meter by second square, and Q is meter cube per second, and HF is meter. So what is the unit of power here? kg. This will give us Newton, and these two get cancelled, meter cube and meter cube, and Newton meter per second cube. Newton meter is joules actually, but what happened? Actually, it is watts. Joules per second. Something is wrong. Hmm. Just give me a minute. Okay. This second square went right. I am just I'll write units here. Units. So it is kg by meter cube, meter by second square, and it is meter cube per second, and it is meter. So it is basically kg, and this becomes Newton, and meter cube get cancelled, so it is Newton meter per second, or else it is watt. So we are getting the final unit. Like this you can cross check if you forget any formula. So formula is this. So P is equal to rho g into Q into HF. So we know everything. 1000 into 9.81 into 0.02 meter cube per second into HF is 12.95. So on multiplying all these terms, what are we getting? 2540 plus 79 watts. Or in the question it was asked that we should give the answer in kilowatts. So it is 2.54 divided by 1000 and it becomes kilowatts. So 2.54 kilowatts. So that is for question 4. Now we'll go to question 5. What is asked in question 5? Glycerin with viscosity 1.4 kg by meter second, specific gravity 1.2, flows through a 1 meter long smooth 10 centimeter diameter horizontal pipe. The maximum pressure drop for which laminar flow is expected is dash. So what is given is that we are told that we have a 10 centimeter diameter pipe which is 1 meter long, and it is a smooth pipe and it is a horizontal pipe, and glycerin is flowing through it, and its viscosity is 1.4 kg by meter second, and its specific gravity is given as 1.2. So specific gravity 1.2 means what is the density? Density will be into 1000. So it is 1200 kg by meter cube. So glycerin viscosity is known, density is known, and the pipe in which the glycerin flows has a diameter of 10 centimeter and length of 1 meter. So what is the maximum pressure drop for which we can expect the laminar flow? So to calculate the pressure drop, we'll see in what ways we can actually get the answer. So first let us write the given. So dynamic viscosity of glycerin is 1.4 kg by meter second. Specific gravity is 1.2, density is 1200 kg by meter cube, and length is 1 meter, and diameter of pipe is 10 centimeter, and it is a horizontal pipe. So these are all the things given directly in the question. So these are direct information. So we are asked that which is the maximum condition wherein we can see the laminar flow. So when is the laminar flow observed, like maximum condition? It is like if Reynolds number is less than or equal to 2300, we can say the flow is laminar still. So that is the maximum in which we can talk about a laminar flow condition in a circular pipe flow system. So laminar flow occurs if Reynolds number is less than or equal to 2300. So what is Reynolds number? Reynolds number is equal to rho v d by mu. So rho v d by mu, and we know mu, and v we can calculate, and d is also known. So if we keep Reynolds number as 2300, that is the maximum possible limit, and we keep everything else which are known and substitute in the equation. What we will be unknown, v will be unknown still. So it is 2300 into mu by rho into d, re into mu by rho into d. So re here is 2300 into mu here is 1.4, and divided by 1200 density, and into d is 10 centimeter or 0.1 meter. So now what we need to do, we need to like calculate whether it is coming out rightly. It is 26.83 meter per second. Now in the question, what are we asked to find out? We are asked to find the pressure drop, so in kilopascal. So if we go back, the maximum pressure drop for which laminar flow is expected is dash kilopascal. So keeping that in mind, what are we going to do? RE is known. Now we keep rest all unknown, and we can get the value of V. So 2300 into mu by rho into d. So that gives us 26.83 meters per second. Now we need to, what are all the other things we need to know? We need to know like if you are planning to use a Darcy equation or something, we need to know the A as well. So A is the cross sectional area of the pipe. So it is pi by 4 d square. So d here is 0.1 meter. So based on that, we can calculate the cross sectional area of the pipe. So it is 3.14 into 0.1 square divided by 4, which gives us 7.85 into 10 power minus 3, or it is 0.00785 or 79 meter square. So since it is a cross sectional area, its unit is meter square. Now volumetric flow rate Q. Why are we calculating all this? Because in Hagen-Pauli equation we need to know the value of Q. That's why we are calculating all these things. So volumetric flow rate Q is equal to area into Vmax. So area we calculated in the previous step as 0.0079 into Vmax. So it is meter square into meter per second. So it becomes meter cube per second. So we can get the volumetric flow rate. So it is A is 0.0079 into Vmax, that is 26.83. That will give us the flow rate, volumetric flow rate. Which is nothing but 0.2106 meter cubes per second. For laminar flow, we can use Hagen-Pauli equation or Darcy-Weisbach equation. So delta P is equal to 128 mu into L into Q divided by pi d power 4. Actually in previous problem also I wrote it as 4. So in one more problem I wrote it as Where did we find power? Okay, and not a direct thing, but yeah, still. So it is 128 mu into L into Q into pi d power 4. So it is 128 into 1.4 into 1 into 1 is length of bed. Q here is 0.2106 divided by 3.14 into zero point 0.1 to the power of 4. Point, okay, 3.14. So it is 120,000 and 190. So basically it is 1,20,000 and 190 pascals. But in the question, if you remember correctly, we were asked to give the answer in kilopascals. So it becomes 120.19 kilopascal. We just divided it by 1000. Okay. Now we'll go to next question. So I hope it is clear. I'll just give a quick briefly discuss what are all the things we saw in the first 5 problems, because I think I confused in the beginning. I confused you people. So first question, it was about finding the direction of the flow of water from between 2 points. So we found out that even though point B is higher than point A, pressure at point A is greater than pressure at point B. So we can say that direction of fluid flow will be from like higher pressure region to the lower pressure region. So based on that, it is from A to B. So that is what we analyzed using different approaches, and also we saw like how the pressure between 2 points are from, we calculated it using the manometer, those things and all, and we got the answer. So that is for question 1. Next question is, a flow is assumed to be laminar. What is assumed to be laminar? If it is at higher Reynolds number, it ideally won't be a laminar flow, but here we are it is mentioned that it is assumed to be laminar. So we are asked to find the friction factor. So for laminar, friction factor is given by 64 by Re, and since it is assumed to be laminar, we can calculate Re and we can substitute in the formula directly. So for calculating Re, what do we need? We need a rho V d by mu. So rho and mu are fluid properties. V is the velocity with which it flows. So we can get it using Q by A, flow rate divided by cross sectional area, and that gives us velocity. And last one, D, is the geometric property, so that gives us Reynolds number, and later substituting into F is equal to 64 by Re will give us the friction factor. Sorry. So next question is head loss in meters. So we have a formula wherein we can do the direct substitution. HF is equal to FL square by D into 2 into G. So we know everything over here, FL square V and D and G. So we just substituted and got the answer. And for question 5, what we got, we are asked to find the power required to drive the flow of water from a pipe that has the flow rate of 0.02 meter cube per second, and friction head is 12.95 meters. So power is nothing but P is equal to rho Q G into HF. So HF is given directly in the question, Q is also given directly. Rho is for water, we know is 1000 kg per meter cube, and G is 9.81. So substituting will give us the answer. Next is the 5th question, wherein we are told about maximum pressure drop. for which laminar flow is expected. So maximum velocity under which the laminar condition will be maintained, that we should see. So Re is rho v d by mu, and for laminar condition Reynolds number will be less than or equal to 2300. And if we maintain that condition, what we can do, we can find the velocity. Re is equal to rho v d by mu, so v is equal to re into mu by rho into d. So that gives us velocity, maximum velocity, and we can calculate the cross sectional area of pipe. Both of them gives us the volumetric flow rate, and after knowing the volumetric flow rate, we can substitute in the pressure drop formula, and we can get the final solution. So these are the main problems. So now we will like move to other problems and see them. Ammonia at 20 degrees Celsius flows through a pipe at 0.005 meter cube per second with a friction head loss of 20 meter. The power required to drive this flow is dash. So what is given is we are now sending ammonia at 20 degrees Celsius and through a pipe who's having a 0.005 meter cube per second flow rate, and the friction head loss is given as 20 meters. So we are asked to find the power required to drive this flow. Again, it is similar to the last problem which we saw. Power is equal to rho into G into Q into HF. So rho we need to find for ammonia at 20 degrees Celsius. Q is given, G we know, HF is given. So first we need to find out what is the density. Given is volumetric flow rate, Q is given 0.005 meter cube per second. Second, friction head loss is HF is 20 meters and temperature is 20 degrees Celsius to find density. And acceleration due to gravity, G is given as 9.81 meter per second square. And from standard reference, the density of ammonia at 20 degrees Celsius is approximately 609 kg per meter cube. Like while you are solving the problems, I request every one of you to find the standard reference and get values checked once again, because I did it in a hurry. So while you are submitting assignments, check once again. So that is my request. Formula is P is equal to rho G Q into HF, and everything we know now, so we can directly do the substitution. So P is equal to 609 kg per meter cube, G is 9.81 meter per second square, Q is 0.005 meter cube per second, and HF is 20 meters. So directly substituting all these values gives us 597.43. 609 into 9.81 into 0.005 into 20. 597.429, we can round it off into 2 digits, 597.43 watts. Here it is not in kilowatts, and in the question also it was not asked about kilowatts. So we can give the answer directly in watts. So power required to drive this flow is dash watts. So we can directly get the value substituted. So that is for question 6 actually. Now we'll go to question 7. Benzene at 20 degrees Celsius is to be transported through a 1 meter long smooth 50 centimeter diameter horizontal pipe. It is desirable to obtain maximum flow rate but maintaining laminar flow conditions without moving to transition or turbulent flow conditions. The maximum pressure drop for which laminar flow can be obtained is dash. This is dash Pascal. This is similar to the problem which we saw around 5th one, I guess. So here again what is given, we are transporting benzene which is at a 20 degrees Celsius through a pipe, and the pipe diameter is 50 centimeter and its length is 1 meter long, and we are mentioned that we have to maintain the condition in the laminar flow condition. It is neither transition or nor turbulent, but it is maintained at laminar flow condition. So at the maximum laminar flow condition, what is the maximum pressure drop? So that is the question. So what is given? Pipe length is given as 1 meters. So it is similar to the problem which we saw, just numbers are different. So a procedure is same actually. So solution, pipe length is 1 meter, pipe diameter is 50 centimeter or it is zero point 0.5 meters. Flow is laminar, so Reynolds number is less than or equal to 2300. Pipe is horizontal and smooth. And viscosity and density of benzene at 20 degrees Celsius, we have to take it from some standard reference. So viscosity is 0.00065 Pascal second. Again, cross check these values, like I don't know from which source I took. So while you're solving your assignment problems, I know similar problems are existing. Wherever I took, I didn't put reference also. So just understand that I took it from somewhere, but I don't know where. So, or else I can check now also, like benzene viscosity. I'll check once again because I don't want to give you wrong information. Benzene viscosity. Okay, it is 6.6 into 10 power minus 5. Oh, no, 10 power minus 4. Yeah, 0.66 millipascal second. Here also, if we go to millipascal, it is 0.65. Yeah, it is 0.65 millipascal second. And its density is to 879 kg per meter cube. It is 876. Okay, like slight variation, but whatever you are using for assignment submission, take the value from a standard reference. So density, and now what we have to do, we are asked to find the maximum pressure drop that we can obtain in the laminar flow condition. So first we need to know the velocity at which, maximum velocity at which laminar flow exists, and therefore Re is equal to rho v d by mu. It should be less than or equal to 2300, and Vmax is therefore a Reynolds number into mu by rho into d. So it is 2300 into 6.5 into 10 power minus 4 divided by rho. Rho is 879 into 0.5. Was it 0.5? Yeah, 0.5. Now after simplification of these numbers, what will we get? 0.00065 divided by 879 divided by 0.5. So it is 3.4 into 10 power minus 3, or it is 0.0034. Now cross sectional area we need to find. It is pi by 4 d square. So again pi by 4 into 0.5 square divided by 4. 0.1963 meter square. Next what we need to do, we need to find the volumetric flow rate. Q is equal to V into A. So it is 0.1963 into 0.0034. It is 6.67 into 10 power minus 4, or 0.00067. 0.067. Now we can actually reduce it. So now we need to like use the Hagen-Parshley equation, and it is 128 mu into L into Q divided by pi d power 4, and on substitution what will we get? 128 into 0.00067 into 1 into, oh, this is for viscosity, that is for flow rate. 0.00065 divided by 3.14 divided by 0.5 to the power of 4. It is 2.8 into 10 power minus 4. This many numbers we don't require actually. 2.84 into 10 power minus 4. That is question 7. So it is a straightforward problem wherein we are asked to find the maximum pressure drop which we can obtain in the laminar flow. And we saw that to get the laminar flow, I mean pressure drop, we need Q. And to get Q, we need V. And to get V, we need the Reynolds number assumption. So based on that, we did the calculation and we got the pressure drop value. So that is for question 7. Uh, so before moving to question 8, I would like a small break. Time is 3:57. We'll meet back by 4 2. We'll come back by 4 2. We'll start now. I hope you are there. So yeah. So this question is similar to the question which we saw in the first problem, finding the direction of flow. Water is flowing in a pipe at 3 meter cube per hour between points A and B. A mercury manometer connected between these two points give a reading of 65 mm. Pipe is 1 centimeter in diameter while length of the pipe between points A and B is 100 meters. However, the pipe is not horizontal but rather point B is 40 centimeter below the point A. It is given that pressure at point A is higher than at point B. Assume room temperature. The direction of flow is from dash. Without even looking at the options for this question, we can directly answer because two major information is given. Leave all the statements. We have that pipe is not horizontal. Point B is 40 centimeter below point A. So point A is at a higher elevation. Second thing is pressure at point A is higher than at point B. So again these 2 points pushes us towards the answer that uh, A to B is the direction of flow. Water flows from point A to point B. So that is the answer. We'll now see how actually. Water is flowing in a pipe at 3 meter cube per hour between points A and B. So we are given the flow rate and we are given mercury manometer connected between these 2 points, and mercury manometer reading is also given. Pipe diameter is given and pipe uh, length is also given. Okay, we'll now start. Option, the direction of flow is from option A from A to B, option B from B to A, option C not enough information provided to predict the direction but the direction is not needed for calculations, option D it can be either way but the direction is not needed for calculations. Both these statements are kind of false because it is in the question enough information is already provided and it cannot be either way. So both C and D are wrong. It can be either A to B or it can be B to A. So we have to choose one based on the statements. So but we know now that elevation is also pushing the flow from A to B and pressure difference is also pushing the flow from A to B. So answer is option A. A is the right answer, from A to B. So if you look at quickly take a look at it. Length of pipe is 100 meter, diameter of pipe is 1 centimeter, and flow rate is 3 meter cube per hour. So 3 meter cube per hour, if we convert into meter cube per second, it is 3 by 3600 meter cube per second, which gives us 3 divided by 3600, 8.33 into 10 power minus 4 or 0.0008 meter cube per second. And vertical drop, that is elevation height, is ZA is higher than B. So it is 40 centimeter difference or 0.4 meters. Manometer reading is 65 mm or 0.065 meters. And density of water is 1000 kg per meter cube. And density of mercury is 13,600 kg per meter cube. And dynamic viscosity of water is 0.001 Pascal second. Gravity is 9.81 meter per second square. So now what we need to do, we need to manometer reading, actually from that we can calculate the pressure difference. So first PA minus PB is rho GH, and here this rho is for density of mercury. so Hg, and Gh. So H is 0.065 and G is 9.81 and it is 13,600. So it is 8,672.04 pascals. Since pressure at A is higher than at B, mercury column height corresponds to this difference, and yeah, it is 8,672.04 pascals. And flow direction based on pressure difference and elevation difference. Bernoulli's equation points between A and B. So it is we are just writing the Bernoulli equation and we are assuming the velocity negligible, and what we get hf. Okay, all these things are not readed. So what we get is PA minus PB is equal to, we are neglecting velocity, so it will become rho g ZB minus ZA plus HF. So now rho g ZA minus ZB, if we calculate separately, actually this is also not needed, but anyways, I'll put it together actually. This is also not needed. So it is rho g ZA minus ZB is, again if we take values, right, it is 1000 into 9.81 into 0.4. 3924 pascals. Pressure drops from A to B. Elevation also drops from A to B. Net pressure difference confirms A is at a higher pressure. Flow is from A to B, and flow occurs from high total head to low total head. So it is A to B is the right answer. So option A is the right answer. Now we'll go to question 9. Average velocity of water in the pipe is dash meters per second. So we are asked to find the average velocity of pipe. So what is given in the question? If we go and look at the problem statement, we are having Q 3 meter cube per hour, and pipe cross sectional area is given. I mean, we can calculate cross sectional area because pipe diameter is given. So with these two information, what we can do, we can get the velocity. We have to go to 9th question. So first let us find the cross sectional area of pipe. So it is pi by 4 d square, and d is 1 centimeter. Oh, d is 1 centimeter. So it is 0.01 meter. We can actually, take and put it. These two. So V is pi by, sorry, A is cross sectional area is pi by 4 d square, and V is Q by A. So 3.14 by 4 divided by 4 into 0.01 square. That gives us 7.85 into 10 power minus 5 meter square, and Q is 0.0008 divided by this value gives us 10.19 meter per second. So the average velocity of water in the pipe is 10.19 meters per second. Going to question 10, the manometer reading will be option A, inversely. Okay, I shouldn't have shown you the answer. Manometer reading will be dash, inversely proportional to head loss. Option B will be a constant. Option C will be proportional to the square of the head loss. Option B will be proportional to the square of head loss. Option E, none of the above. Actually, option E is the right answer. It will be none of the above because manometer reading will be directly proportional to head loss. Option E, none of the above is the right answer. And going to question 11. Once again. Just give me a minute. Anyways, okay, Reynolds number describing the flow is dash. And it is option, okay, we need to calculate it. So Reynolds number is Re is equal to rho V d by mu. So rho is again like for density of water. V we calculated, not here. V we know, d we know, mu also we know. So just substituting it will give us the answer. So Re is equal to rho V d by mu. So rho is 1000, V is 10.19 meter per second, which we calculated in the 9th question, and d is 1 centimeter. So it is 0.01 meters divided by mu. So mu is 0.001 for water. So these are all for water. So after that, if we substitute it, what will we get? 10.19 into 1000 divided by 0.1. So it is 101,900 or 1,01,910. So that is the Reynolds number. So Reynolds number describing the flow is therefore 1,01,910. Now moving on to question question 12. If flow is assumed to be laminar, imagine you are in a world of zero disturbances and you have Atomically smooth pipe that flow can remain laminar for any Reynolds number, then the friction factor can be calculated as dash. So what is asked is that we are assuming the flow to be laminar because we got the Reynolds number as 1 lakh something, and that is not a laminar flow condition, that is a turbulent flow condition. But imagine we are in a world of zero disturbances and we have a flow that can remain laminar for any Reynolds number, then what will the friction factor be? So if it is a laminar flow, what will the friction factor be? It is like 64 by RE. So now in our case it is 64 by 1 lakh 1910. So options are option A 0.00018, option B 0.00063, option C 0.0009, option D 0.009. E option is 0.000036, F is 0.000063. Oh, option B 0.00063. Okay, I think no. Yeah. Okay. It is 64 by 1019 and 10. 6. Yeah. 0.00063 is the right answer. Option B is the right answer. So how Reynolds number we calculated, and RE is equal to Reynolds number and friction factor is equal to 64 by RE, that is Reynolds number. So direct substitution will give us 6.28 into 10 power minus 4. So our answer is 0.00063. That is for question 12. Moving on to question 13, what we have is the pressure drop across A and B is dash Pascal. Okay, now we have to find the pressure drop across A and B points. Manometer reading is given as 65 mm and manometer fluid is mercury and density of mercury is 13,600 kg per meter cube and acceleration is 9.81. So formula is rho gh or rho mercury density into G into H. So it is just a direct substitution. So what we can do, 13,600 into 0.065 into 9.81, 8,672.04 Pascal is the right answer. So it is a direct substitution only. That is for question 13. Now for question 14, what we have is head loss in meters is dash. So HF is equal to delta P by rho G. So delta P we calculated in the last slide as 8672.04 divided by rho is 1000 here and G is 9.81, so that gives us 0.884 meter. So HF is 0.884 meters. Okay, now it is not a direct question, 15th question. So we are just going to see. Explain the figure given. So we have a flow, pipe flow. So we are what we are going to do is we are just going to explain what each region denotes. So first one is it is a growing boundary layer, right? Like what happens is we are having a fluid that enters into the pipe flow and it starts building the flow profile, and here we have a fully established flow profile, and it is like so we have to explain the figure here. So this is the pipe and this is the velocity profile, and the velocity is a function of r and x, so it is x and it is r is the radius and x is the length in that axis. So we'll just see what each denotes. So A is growing boundary layers. So right after the water enters the pipe, the fluid velocity is kind of uniform here, but thin boundary layers begins to grow along the pipe walls. These controlled regions are where viscous effects slow the fluid near the wall. So we just give conditions, right? Near the walls, the velocity will be kind of equal to the walls. That is kind of a zero velocity. Based on that only, mostly the no slip boundary condition and only works. If you are familiar with the CFD concepts, you will be knowing that. But anyways, like growing boundary layers, like after immediately after the water has entered the pipe, fluid velocity will be uniform, but near the walls the boundary layer begin to grow, and these controlled regions are where viscous effects will be there and they slow the fluid near the walls. And second is inviscid core flow, and the central region of the pipe near the entrance is mostly unaffected by viscosity. Fluid velocity remains almost uniform here. Once again, so here central region is mostly it is here wall near walls the viscosity effects will be there, but in the inner core region it will be unaffected by viscosity. So fluid velocity remains almost uniform over here and in the core region. And next is the here where the boundary layers merge with increasing distance from the entrance. The boundary layers on the opposite sides of the pipe grow and eventually merge when the viscous region meet at the center. So this region, and oh, I didn't want, why, yeah, I don't want. D is the developed velocity profile and fully developed profile. After merging, the entire cross section is influenced by viscosity, leading to the fully developed flow profile. And this is parabolic for the laminar flow. So here we are seeing a parabolic profile, right? It is for the laminar flow. The profile shows no longer any changes. What is fully developed flow? After that, it is independent of the change in distance. The flow profile is independent of change in the distance. It remains the same at all the distance that follows. And next is we have E is entrance length. So this is the distance from the pipe inlet to where the boundary layers have merged and fully developed flow starts. That is known as the entrance length, and depending on Reynolds number and the pipe diameter. And F is the fully developed flow region. So D is developed velocity profile, like the distance is fully developed flow region. Beyond the entrance length, after like till the point of entrance length, there will not be developed velocity profile. Beyond that entrance length, the flow will be fully developed, meaning velocity profile remains constant along the pipe, and all changes are like due to pressure drop only. So that is for question 15. Now we have a last problem for today's session, but this problem is kind of I think this is the last. Yeah, this is the last problem, but we just have combined all the concepts and we have given a single question. Okay. It is like water flows through a 50-meter long, 1 centimeter diameter smooth pipe, and flow rate is 2 meter cube per hour, and pipe is inclined such that B is 30 centimeter below point A, and a mercury manometer connected between A and B shows a reading of 55 mm. Oh. Assuming water at room temperature and that pressure at A is higher than at point B. So what is given? We have a water flowing through a 50-meter long and 1 centimeter diameter pipe. Flow rate is 2 meter cube per hour and pipe is inclined. So point B is 30 centimeter below A. And connected between 2 points, we have a manometer whose reading shows 55 mm. Assuming water at room temperature and pressure at A is higher than at B. So what will be the flow direction? The flow direction will again be from A to B, because it is given that pressure at A is higher than at pressure at B. So because of that, and also it is given that pipe is inclined, the inclination is also in such a way B is lower than A and it is 30 centimeter. So always the flow will be from, in this context, it will be flowing from A to B. So that is for, if question is asked regarding the flow, direction flow, we need to give that. But let us see what is asked in the question first. So we are having few questions, we need to solve them. Okay. First one, calculate the average velocity of water in the pipe. Second one, determine the Reynolds number for the flow. Option C, assuming the flow remains laminar, ideal condition, calculate the Darcy friction factor. Option D, find the pressure drop between points A and B using manometer reading. Option E, calculate the head loss between points A and B. Option F, using the head loss, compute the actual Darcy friction factor for the flow. So what is given is that we are having a scenario which is similar to the problems in the previous question. So nothing new is here, just a change in numbers. So what is given? We are having a flow, 2 points between which the flow is happening, and we know the length and diameter of the pipe in that area, and we also know the flow rate, and we know that B and A are not in the same plane. They are in a B is slightly down from A, and also we have a mercury manometer connected between A and B, which shows some reading indicating the pressure drop. And what else is given? Pressure at A is higher than at B. These are all the information given. So now what we have to find? First we have to find the average velocity, and using average velocity, what we can do? We can get the Reynolds number. Reynolds number is equal to rho v d by mu. How can we get average velocity? Average velocity is equal to flow rate by area, cross-sectional area. Flow rate by cross-sectional area gives us the average velocity, and average velocity into rho into d by mu gives us a Reynolds number. And third is, assuming laminar condition, ideal condition, we need to find the friction factor. So that is again 64 by Re. And next we have to find the pressure drop using the manometer reading, that is rho mercury into G into H. And finally we have to calculate the head loss between points A and B, and using that head loss we need to calculate the actual Darcy friction factor. So this is how we are going to do this problem. So yeah, we'll start doing one by one. First one is what is asked. First one was find the average velocity. So average velocity, first let us first see the given first. Length of the pipe is 50 meters. Diameter of the pipe is 1 centimeter. Or like, why to keep 1 centimeter everywhere? Why can't we keep it as 5 centimeter and we'll check. It is 5 centimeter and it is 0.05 meters. So just take how to do from the problem. Don't see the numbers, because as you have seen, I keep changing the numbers just to make the problem a little different. And it is Q is 2 meter cube per hour, or in seconds it is 2, meter cube per second, it is 2 divided by 3600, it is 5.56 into 10 power minus 4 meter cube per second. Vertical drop is 30 centimeter, B is lower, so it is 0.3 meters. And manometer reading is 55 meter mm or 0.055 meters. And density of water is 1000 kg per meter cube, and density of mercury is 13,600 kg per meter cube. And dynamic viscosity of water is 0.001 pascal second, and gravity is 9.81 meter per second square. So those are the things now we have to change. So average velocity is uh, u is equal to q by a. So we know q, we have to find a. So a is pi by 4 d square. So we change it into 5 centimeter. So we have to redo the calculation now. So 0.05 square divided by 4 into 3.14. So it is 1.9625 into 10 power minus 3. Okay. Now with this new area, we need to calculate the velocity. So it is 1.9625 into 10 power minus 3. 5.56 into 10 power minus 4 divided by this one. So our velocity will be reduced because I'll just 5.56 into 10 power minus 4. It is 0.2833. Previously our diameter was low, but flow rate was the same. So since the diameter was small and with the high flow rate, we had a high velocity. But now the same flow rate was maintained, but our diameter was reduced. So sorry, diameter was increased. So the velocity also decreased. Actually velocity decreased. Previously diameter was low, so the to have that much flow rate in that small area, we have the higher velocity. But now since our velocity is not velocity, since our pipe diameter was also high, velocity kind of decreased. So that is the thing. So now it is rho v d by mu. Again it is d, and again it is 0 5. Reynolds number is equal to rho v d by mu, and d is 0.05 and v is, again it is changed, 0.2833 into 0.05 into 1000 divided by 1000. Oh, 1000 into 0.2833 into 0.05 divided by 0.001. 14,165. 14,165. Okay. Now what we need to do, assuming our Reynolds number is calculated as rho v d by mu, and uh, now we have to find the Darcy friction factor, assuming the flow as laminar flow. Flow is not laminar. Flow is turbulent. Like how we saw in the previous problem, flow is turbulent, but we are just assuming it, and it is 64 by RE, 64 by RE. That is Reynolds number. So it is 14165. 4.5182 into 10 power minus 3. That is the friction factor. Or else how we can write 0.0045. 0045 into 1000. This is the same 0.0045. This is our Darcy friction factor assuming laminar flow under ideal condition. Under imaginary condition, no, not even ideal. I will change in question also as imaginary. So our friction was 0.0045. Okay. 0.0045. Now what else was asked? Find the pressure drop between points A and B using the manometer reading. So now what we have to do, we have to use the manometer reading, that is the 55 mm height difference, and calculate the pressure drop between points A and B. Uh, so that is what we are going to do. So delta P is equal to rho GH. So here rho is the density of mercury. So it is 13,600 into 9.81 into 0.055. So what we are getting, 13,600 into 0.055 into 9.81. It is 7,337.88 Pascal. So now we calculated the pressure drop between points A and B using the manometer reading, and now we have to calculate the head loss between points A and B, and it is delta P by rho G. So delta P is 7337.88 divided by 1000 into 9.81. That gives us 9.81 0.748 meters. Now we know the pressure drop from manometer reading, and we calculated the head loss between A and B. And finally the original Darcy friction factor, actual friction factor for the flow, friction factor. So F is equal to HF into 2G into D into L D divided by L into U square. So HF is 0.748, there is no change, into 2 into 9.81 into, we changed the diameter of the pipe as 5 centimeter from 1 centimeter, so into 0.05, and divided by L is 50 meters, and our U also got changed, so we need to update the calculation with the new U. So U here is what did we get? U 0.2833 meter per second. So that we can substitute here 0.2833 meter per second square, and now we have to calculate it. I'll just remove this. Yeah. So it is 0.748 into 2 into 9.81 into 0.05 divided by 50 divided by 0.2833 square. Oh, something is wrong. What was the previous value? 0.0059 now. Okay, I'll just do the calculation once again. 0.748 into 2 into 9.81 into 0.05 divided by 50 divided by 0.2833 square. Okay, it is 0.1829. Friction factor is 0.1829, but yeah, it won't be the reality because like I just, in all the problems I change numbers. It might not be following exact physics based on the numbers I gave, because I just want to give a different formula. So the takeaway is, take the approach but don't probe much into the logic behind the numbers. It may not be following in most of the problems, and some, yeah, that is one thing. So yeah, like how to quickly revise 16th problem, we calculated the average velocity from the flow rate formula. Q is equal to A into V. Basically that is what we do everywhere, right? Volumetric flow rate is equal to density into sorry, not density, cross sectional area into velocity. So velocity in return will be volumetric flow rate divided by cross sectional area, and Reynolds number is Re is equal to rho V d by mu. Here when we are talking about a cylindrical pipe or cylindrical thing, d will be the diameter of the pipe, and V is the average velocity, rho and mu are the fluid properties. And third one, assuming laminar condition, calculate the Darcy friction factor, which we did. And finally we found the pressure drop between points A and B using manometer reading. Again it is like from using rho gh, but by using the mercury properties, fluid mercury density, and head loss we calculated, and using the head loss we calculated the actual Darcy friction factor for the flow. So this is how we do question 16. It is similar to the last few problems which we saw earlier. So in today's class, that was the thing which we did repeatedly, and apart from that we saw a theory question from here. There is one more theory question. I hope you people will be able to do it on your own in the assignment. So yeah, that's it for today's class. If there is any doubts, we can discuss now, or else we can close the session. We can meet next Saturday same time. But if there are any doubts, let me know. We can discuss. All the lecture videos and notes will be made available to you. Like, I apologize, once someone was like, I didn't update the permission properly for the notes, but later I updated the permission. Like, if sorry for the inconvenience caused, I didn't realize that. So that is one thing. Yeah, if there are no doubts, we can actually close the session, and we can meet next week at the same time. If anyone knows how to handle this mirroring thing, it will be very helpful. Yeah. So yeah, that's it. I guess we can stop today's sessions. We'll meet again next week, same time. Thank you. I'll close the recording first.